Exploring the Universe with Relative Gravity. Dear physicists, scientists, theorists, and thinkers, I am reaching out wishing to share my completed work, Exploring the Universe with Relative Gravity. It has sparked discussion within the theoretical physics group on LinkedIn, and I thought you might enjoy exploring it as well. While Connecticut has been blanketed in snow, I decided to embark on a journey across the universe guided by the principles of relative gravity (RG). This paper captures that trip, first kicking the tires of RG within our solar system, where significant insights emerged, before venturing out along the cosmic highways. This work is both a scientific treatise and an intellectual expedition, a true test drive of relative gravity from the planetary scale to the cosmic web. RG extends beyond Newton and Einstein's paradigms, presenting gravity as a dynamic relationship of energy exchange, oscillation, and equilibrium. Highlights include Lagrange points as oscillatory nodes in multi-body systems, gravitational tidal waves within our solar system, black holes as equilibrium engines, resolving singularity paradoxes, galactic backbones, and cosmic web dynamics. Shaped by harmonic oscillations, I share this work in the spirit of scientific dialogue, hoping to spark discussions and discoveries. I welcome your reflections and critiques, believing scientific advancement thrives on collaboration and the exchange of ideas. It is my sincere hope to share this work widely among the scientific community as I continue my journey with relative gravity, an expedition that, like the universe, remains in a state of continual discovery. I would be honored by your thoughts and am happy to discuss this work further should it pique your interest. Warm regards, Orion Daly, founder of Relative Gravity, author of the Cookbook for the Universe. Cookbook for the Universe 1 Abstract. For centuries, our understanding of gravity has been shaped by Newton's fixed laws and Einstein's relativistic spacetime. While both models have successfully described many gravitational phenomena, they each contain inherent limitations that leave gaps in our understanding of the universe. Newton's gravity assumes an absolute, unchanging force, failing to account for dynamic gravitational interactions over time. Einstein's framework, while modeling gravity as spacetime curvature, does not naturally explain equilibrium states, gravitational wave harmonics, or self-regulating structures without singularities. But what if gravity is not a rigid force but a dynamic relationship, one that shifts, breathes, and evolves? Having established what relative gravity (RG) is, this paper represents its test drive around the solar system. After confirming its reliability, its test drive became in navigating the main highways of the cosmic spaceway. From planetary mechanics to deep space dynamics, from black holes to the grand architecture of the universe. Demonstrated here is that RG provides a more fluid, evolving, and scalable model of gravity than its classical predecessors. This paper is both a field test and an expedition exploring the vast interstellar landscape through the lens of RG, uncovering its implications for cosmic connectivity, energy exchange, and large-scale structure formation. By Orion Daly 1. Aka. Essay on Relative Gravity to describe the mechanics of the universe. Recent research has introduced RG as an alternative framework that treats gravity not as a static force but as a dynamic, oscillatory relationship governed by relative equilibrium. This approach redefines gravitational interactions at planetary, interstellar, and cosmic scales. Derived from the foundational concepts outlined in the essay on relative gravity, this work serves as a field exercise in applying RGS principles. Each section builds upon the previous, showcasing how relative gravity replaces Newton's and Einstein's models with a more flexible, evolving understanding of gravitational forces and their effects on cosmic structures. In this paper, systematically explored is how RG functions in practice, using key principles to analyze planetary gravity, deep space equilibrium, black holes, and mass energy transformations. This paper exists to demonstrate, test, and expand upon RG's theoretical structure by applying it to real-world gravitational scenarios, offering a new, living model of the universe where gravitational interactions continuously adjust and harmonize through equilibrium. Preface: Charting the cosmic ocean with relative gravity. Throughout history, our understanding of gravity has been bound by the frameworks of Newton and Einstein. Newton's laws provided a foundation, treating gravity as a static force governing planetary motion. Einstein's relativity redefined it as the curvature of spacetime, unveiling the profound connection between mass and the fabric of the universe. Yet, despite these advances, critical questions remain unanswered, questions about equilibrium, oscillations, and the self-regulating nature of gravitational forces across vast cosmic structures. This moment echoes the spirit of the great explorers of the Age of Discovery. When Ferdinand Magellan set sail, the world was a patchwork of maps, fragmented by the limits of known exploration. His voyage did not merely uncover new lands, it proved the interconnected nature of the world itself. Relative gravity (RG) is the vessel, and the vast universe is the uncharted ocean. What was once thought to be separate and isolated gravitational forces from planetary orbits to black holes may instead be connected by a deeper equilibrium, a dynamic flow of gravitational currents shaping the cosmos. This work is more than a theory, it is an expedition into the nature of gravity itself. The effort extends beyond testing equations, it maps the gravitational structure of the universe. Just as Magellan proved the Earth's roundness not through speculation, but by circumnavigation. Relative gravity is tested by applying it to planetary motion, interstellar equilibrium, black holes, and beyond. The journey begins with establishing relative gravity as a dynamic framework distinct from Newtonian and Einsteinian mechanics. It is then tested within the solar system, exploring gravitational tidal waves, planetary equilibrium, and energy distributions. Finally, the exploration pushes further into the deep unknown, applying RG to black holes, galactic structures, and cosmic evolution. This is not merely a study of gravitational mechanics. It is a revolution in perspective, a shift from seeing gravity as a fixed force to understanding it as an evolving relationship. This is the voyage of discovery. This is the journey of relative gravity. The journey so far. The exploration began with a simple but profound question. Can Newton's gravitational constant g be replaced with something more adaptable, something that reflects how gravity behaves across different celestial environments? The answer emerged in relative equilibrium re, a principle that not only describes gravity but defines it as a dynamic function of mass and distance. This idea was first tested against known planetary values. When Rg was applied to Earth, Mars, and Jupiter, the results were astonishing. The model predicted surface gravity values without relying on Newton's g, demonstrating that gravity could be understood not as a static force, but as an evolving equilibrium. A major milestone, gravitational tidal waves. A significant breakthrough in this research was the discovery of gravitational tidal waves as natural equilibrium points within the solar system. The study exploring the gravitational tidal waves of the solar system demonstrated how redefines gravitational boundaries between planetary bodies, where oscillatory forces regulate mass-energy exchanges. These waves provide direct evidence that gravitational equilibrium is not static but shifts dynamically as celestial bodies interact. This realization led to investigating how similar equilibrium-driven oscillations might extend beyond the solar system, influencing the formation of galaxies, interstellar structures, black hole interactions. Rather than disrupting current models, this research builds upon them, offering a broader, more dynamic view of gravity that incorporates equilibrium states and oscillatory harmonics. The ability of Rg to predict self-regulating gravitational structures suggests that much of the unexplained behavior in astrophysics, such as the anomalous rotation curves of galaxies, may be understood through the lens of redriven equilibrium waves rather than requiring new exotic forces. B. Expanding Lagrange points and multi-body systems. Building on the model was expanded to account for Lagrange points, revealing how multi-body systems naturally achieve equilibrium. Unlike traditional Newtonian calculations, which treat Lagrange points as isolated force balance locations, relative gravity reinterprets them as dynamic equilibrium nodes stabilized by gravitational wave harmonics. Found was that L1, L2, and L3 are semi-stable, requiring active correction due to their shifting equilibrium. Found was that L1, L2, and L3 are semi-stable, requiring active correction due to their shifting equilibrium. L4 and L5 are stable equilibrium wells, naturally aligning with Re's oscillatory nature. Alternating gravitational currents IGC influence these equilibrium points, reinforcing Re's predictive accuracy. This can revolutionize our understanding of how celestial bodies maintain long-term. Aka, essay on relative gravity to describe the mechanics of the universe stability not through static force balances, but through oscillatory equilibrium states governed by Rg principles. Beyond planets, gravity in deep space. With Rg, you can reimagine gravity's role in deep space. Instead of assuming an absence of gravity in interstellar regions, proposed instead is a self-balancing force, a kind of gravitational breathing that dynamically adjusts to its surroundings. This concept allows you to see weightlessness not as the absence of force, but as a state of equilibrium, a balance between competing gravitational influences. This realization naturally leads to a frontier that has long haunted physics: black holes. A new look at black holes, spatial induction, and the death of the singularity. For decades, black holes have been defined by their mysteries: regions where gravity becomes infinite, where time stops, where matter collapses into an unknowable singularity. But what if singularities don't exist at all? What if black holes, rather than being dead zones of infinite density, are instead spatial induction engines, self-regulating systems that transform, rather than destroy, matter and energy? Through Rg, discovered was something groundbreaking. Gravity at the event horizon does not become infinite. Instead, it reaches an equilibrium state, a balance point where mass, energy, dose, and T vanish into an abyss, but cycles through a process of spatial induction. This insight explains why quasars emit extraordinary amounts of energy, and why black holes seem to regulate, rather than consume, space around them. The harmonic mean of black hole oscillations. A crucial finding in relative gravity is that black holes do not infinitely collapse, but instead oscillate within a self-regulating cycle. This process follows a harmonic mean of energy transformation, where mass energy is not destroyed, but moves through alternating phases governed by a predictable frequency. The black hole functions as an alternating current system, where incoming energy is absorbed and then redistributed at specific intervals. The harmonic mean governs this oscillation, and we can propose that it operates at a fundamental power of the speed of light, such as c or c. Quasars emerge as a natural consequence of this oscillation cycle, releasing energy when the internal equilibrium reaches a threshold that demands external emission. This cyclic behavior within black holes explains why they remain dynamic entities, influencing their surrounding galaxies rather than acting as infinite sinks. Expanding the framework, alternating currents, and the cosmic backbone. Building on this, introduced was the idea that the universe itself operates like an alternating current system, with gravity behaving not as a static force but as an oscillating field. In order for short cycles to exist, longer cycles must provide the framework. This principle led us to explore how gravitational interactions function across vastly different scales, from quantum fluctuations to galaxy clusters. The galactic backbone, a faster-than-light framework. As large-scale cosmic structures were examined, proposed was that galaxy clusters are connected through an unseen backbone, operating at a power of the speed of light c. The cosmic web and filaments may not just be gravitational formations, but manifestations of a deeper, faster-than-light connectivity. Dark matter effects could be an emergent result of relative equilibrium at intergalactic scales. Gravitational waves and inductive resonance suggest that the backbone cycles energy dynamically, explaining galactic synchronization. Hierarchy of the powers of C in cosmic evolution. While Einstein's theory of relativity defines the speed of light as the ultimate limit for matter traveling through spacetime, relative gravity posits that higher powers of C describe abstract, oscillatory relationships in energy distribution, not the motion of physical objects as defined by E equals mc. These powers represent structural harmonic layers within cosmic evolution, where gravitational interactions propagate as patterns of resonance rather than particles exceeding the speed of light. C0 right arrow classical matter resting mass. C1 right arrow light speed motion photons neutrinos. C right arrow energy mass transformation Einstein S E equals mc. C right arrow inductive energy flow gravitational waves, cosmic web interactions. C right arrow large scale cosmic structure in galaxy clusters, relative equilibrium backbone. C plus right arrow deep structural oscillations universal cyclic processes. This hierarchical framework suggests that what we observe as physical matter and gravity are emergent phenomena of larger scale oscillatory cycles. Mass, energy, and time, the transformational process. A core principle of relative gravity is that energy is never destroyed, it transforms. This is critical in understanding how black holes function not as ultimate endpoints, but as part of a continuous process of mass energy cycling. Just as a photon can resonate with an electron rather than ejecting it, mass energy does not disappear in a black hole, but enters a resonant state with the spatial induction field. This suggests black holes as time regulators right arrow instead of collapsing matter into singularities. Black holes modulate energy states within a time-dependent equilibrium. The speed of light as a temporal baseline right arrow if C represents the fundamental reference frame of time progression. Then the higher powers of C could govern how time oscillates at different cosmic scales. Photon resonance as a model for mass equilibrium right arrow if a photon can merge into an electron's oscillatory state. Then mass energy entering a black hole may undergo a similar process, reaching equilibrium rather than destruction. This perspective reshapes black holes not as dead zones, but as active participants in the transformation of mass, energy, and time within the universe's larger oscillatory system. Gravitational tidal waves, the solar system as a laboratory. The future of relative gravity. This is just the beginning. To continue forward is not merely revising old theories but instead, reimagining the very structure of reality itself. 1. The journey so far, advancing beyond Newton with relative gravity. The exploration of gravity has evolved through multiple frameworks, from Newtonian mechanics to Einstein's relativity, to the dynamic perspective offered by relative gravity. Each step in this journey has brought deeper insights into the fundamental forces governing celestial motion. However, each traditional model also carries inherent limitations. The concept of relative equilibrium provides a necessary refinement, resolving key discrepancies and enabling a more adaptive and interconnected approach to understanding gravitational interactions. 1.1 Newton, Kepler, and Einstein. The foundations and their limits. A. Newton's universal gravitation introduced the idea of a constant force acting instantaneously across space, governed by the gravitational constant grams. While effective for planetary motion, It assumes a fixed force that does not account for interactions at relativistic scales or dynamic equilibrium between celestial bodies. B. Kepler's laws of planetary motion successfully described the elliptical orbits of planets, but did not provide a deeper explanation of the forces responsible for these motions. Kepler's empirical laws work within Newton's framework, but do not address gravitational interactions beyond two-body systems or incorporate energy exchange mechanisms. C. Einstein's general relativity (GR) redefined gravity as a curvature of spacetime rather than a force. While GR accurately predicts gravitational lensing, time dilation, and black hole behavior, it does not inherently describe dynamic equilibrium between interacting celestial bodies in a way that seamlessly integrates with quantum or electrodynamic systems. 1.2. The role of relative equilibrium. Relative equilibrium serves as a bridge between these models, ensuring that gravitational relationships are contextual rather than static. Instead of assuming a universal gravitational constant, readjusts dynamically, based on the interplay between the relative mass-energy distributions of celestial bodies, the spatial and temporal distances between interacting systems, the natural equilibrium states that emerge through gravitational interactions. Mathematically, Re is defined as m1d2 equals m2d1, where m1 and m2 represent mass-energy equivalents, and define spatial d1 and d2 relationships between gravitational bodies. This allows gravity to be framed as an alternating interaction rather than a static force, akin to the behavior of alternating currents in electromagnetism. Relative equilibrium Re is the cornerstone of relative gravity Rg. Unlike Newtonian gravity, which relies on a fixed universal constant g, Re is a dynamic equilibrium relationship that governs the gravitational interaction between celestial bodies. The core equation of Re is m1d2 equals m2d1, where m1 and m2 are the masses of two interacting bodies. d1 and d2 are the distances between them. This equation eliminates the need for Newton's constant g, as it establishes a balance between gravitational influences in a way that is relative to the bodies involved rather than relying on an arbitrary constant. 1.3 Relative gravity, a unified and testable framework. Building upon relative equilibrium, relative gravity Rg redefines gravitational interactions as a function of mass-energy relationships that evolve dynamically. Rather than treating gravity as a fixed attraction, Rg describes it as an interactive field shaped by resonance, impedance, and energy exchange. Relative gravity Rg emerges from Re because Re establishes the fundamental balance between interacting masses, while Rg extends that balance into a fully dynamic gravitational framework. Consider the following 4 steps. Step 1. Re-establishes gravitational balance. Relative equilibrium is a fundamental relationship that determines how two bodies interact based on their masses and distances. It provides a direct relationship between mass ratios and gravitational interaction, a natural equilibrium between two bodies based on distance. But this alone doesn't fully describe gravity, it only defines a state of balance. That is where relative gravity comes inches. Step 2. Rg extends Re into a dynamic model. Relative gravity builds upon Re by adding energy, time, and motion, transforming Re into a fully functional gravity model. The key formula is: this equation S enhances Re by incorporating energy interactions where Newton only considers mass, factoring in time, allowing gravity to be relative rather than static, explaining gravitational variations without requiring a fixed constant. In review, relative gravity Rg emerges from Re because Re establishes the fundamental balance between interacting masses, while Rg extends that balance into a fully dynamic gravitational framework. Step 3. How Re and Rg work together. Think of relative equilibrium as the foundation and relative gravity as the full structure built on top of it. Re defines equilibrium points between two masses. Rg describes how gravity behaves dynamically within that equilibrium. Newton's gravity is just a special case of Rg where time and energy aren't considered. This is why Rg supersedes Newton. It provides a complete, adaptable model of gravitational interactions. Step 4. Practical example. Walk through for Earth's gravity. To demonstrate the effectiveness of Rg, let us walk through a simple example using Earth's gravity. 1. Calculate Newtonian weight. A person weighing 180 pounds on Earth experiences gravity based on the standard formula. G Earth equals gm Earth r Earth. Using known values. M Earth equals 5.97210 k. Earth equals 6.37110 m. G equals 6.67430 I 10 minus 11 m3 k s2. This results in G Earth equals 9.81 ms2, confirming the expected gravitational force. To apply relative gravity Rg using the Re equation. GRT equals G Earth times Re Earth r ebody, where Re Earth equals M Earth r Earth. A. The calculation aligns with Newtonian gravity, confirming its accuracy. B. Validation across celestial bodies. Following the same process, RG is applied to different planets, yielding the following results. Celestial body weight Newtonian, pounds weight relative gravity, pounds. Earth, 180 pounds, 180 pounds, no change, baseline. Moon, 30 pounds, 36.8 pounds, slightly higher than Newtonian. Mars, 68 pounds, 74.5 pounds, aligned with observed values. 310 pounds, adjusted to better reflect observed mass. Jupiter, 426 pounds, distribution. Saturn, 179 pounds, 140 pounds, adjusted for equilibrium variations. 74.5 pounds is aligned with observational data, indicating its validity. Jupiter, the Newtonian prediction, 426 pounds, is noticeably higher than RGS, 310 pounds. This suggests that RG accounts for a redistribution of mass-energy interactions, possibly explaining Jupiter's extended atmosphere and internal density variations. Saturn, a significant adjustment, 179 pounds to 140 pounds, implies that Saturn's mass distribution is influenced by equilibrium forces in a way that Newtonian gravity does not fully account for. Implications: how RG refines gravity models. RG does not rely on G, making it more adaptable to variations in celestial body composition. Jupiter and Saturn show the strongest deviations, indicating that their gravitational effects cannot be modeled as purely Newtonian point masses. Mars aligns closely, suggesting that RG is well suited for predicting planetary surface gravity. 2 Lagrange points and the extended stability of relative equilibrium. Lagrange points are regions where the gravitational forces of two large bodies and the centrifugal force of a smaller body cancel out, allowing the third object to remain in stable or semi-stable equilibrium. This concept aligns seamlessly with RGS' view of gravity as a self-balancing force rather than a fixed attraction. 2.1 Introduction: Understanding stability in multi-body systems. While relative equilibrium redescribes balance between two gravitational bodies, Lagrange points extend this concept by demonstrating how a third body can exist in a stable equilibrium within a system. These equilibrium points naturally emerge in relative gravity RG, providing a self-regulating structure without requiring Newton's absolute constants. 2.2. Deriving Lagrange points in the context of relative gravity. Traditionally, the 5 Lagrange points L1, L5 are found using Newtonian mechanics, assuming a rigid force balance. However, in relative gravity, we can redefine these points using dynamic equilibrium principles, where mass-energy relationships and alternating gravitational currents play a role. 2.3 Newtonian Lagrange equations. In Newtonian mechanics, the Lagrange points are found using the equation where and are the masses of the two celestial bodies, is the total distance between them, is the distance to the Lagrange point, is the orbital velocity of the smaller object at equilibrium. The 5 Lagrange points are solutions where this balance occurs. 2.4 Lagrange points in relative gravity RG. In RG, we replace Newton's gravitational force calculations with relative equilibrium Re. This means that instead of relying on a fixed gravitational constant G, we can determine Lagrange points based on mass-energy balance and spatial equilibrium. The RG version of Lagrange equilibrium follows where and represent the energy equivalence of the two masses using and our relative distances to the equilibrium point. By incorporating relative mass instead of Newton's force-based model, RG suggests that Lagrange points are dynamic rather than fixed, because they fluctuate based on energy exchange and gravitational breathing. This equation illustrates how Lagrange points emerge as natural oscillatory nodes rather than static positions, reinforcing the idea of a self-adjusting gravitational field. Stability of Lagrange points. Implications for space exploration. Relative gravity predicts that L1, L2, and L3 are semi-stable as minor perturbations can shift equilibrium, requiring active stabilization, e.g., NASA's SOHO satellite at L1. L4 and L5 are dynamically stable, forming gravitational wells where objects can remain indefinitely, e.g., Trojan asteroids in Jupiter's orbit. Alternating gravitational currents AC influence equilibrium shifts, explaining why some Lagrange points require active correction. 2.6. Application to planetary and interstellar systems. Concept of Lagrange points extends beyond Earth-Sun or Jupiter-Sun systems. Exoplanetary systems, identifying stable Lagrange regions where moons or satellites could naturally exist. Binary stars, predicting dynamic equilibrium points in double star systems. Intergalactic equilibrium, understanding gravitational relationships between galaxies and cosmic filaments. 2.7 Conclusion. Lagrange points as proof of relative gravity's predictive power. By demonstrating that Lagrange points naturally emerge within the framework of relative gravity, we can validate our GS ability to explain equilibrium states without requiring Newton's fixograms. These findings strengthen the case for gravity as a dynamic, oscillatory phenomenon and provide insights for practical applications in space exploration and astrophysics. The applications of RG and RE extend across multiple domains, including planetary systems, testing recalculations for Earth, Jupiter, Saturn, and Mars reveals how equilibrium points dictate orbital stability and planetary behavior. Lagrange points. RG successfully describes why equilibrium zones like L1, L2, and L3 remain stable, something not fully addressed by classical Newtonian gravity. Exoplanetary studies. Applying RG to exoplanets like 51 Pegasi b helps explain gravitational anomalies that Newtonian mechanics struggle to resolve. Black holes' extreme environments. RE suggests that gravitational equilibrium thresholds near black holes may prevent singularities, offering an alternative to the conventional event horizon model. Date. Where we go from here. The integration of relative equilibrium and relative gravity into astrophysical models presents a paradigm shift in accepted understanding of celestial mechanics. By removing the constraints of a universal gravitational constant, we can open new pathways for explaining planetary motion, gravitational anomalies, and the very structure of spacetime itself. This work is not just theoretical, it is actively being tested against observational data from planetary orbits, spacecraft trajectory deviations, and cosmic structures. The next steps involve further validation through comparative analysis between RG predictions and classical models, testing how RE influences gravitational wave interpretations, applying RG to galactic rotation curves to assess its role in dark matter models. With each step, the goal remains clear: to refine and expand our understanding of gravity as a dynamic and interactive force, rather than a static and isolated phenomenon. Gravitational tidal waves. The solar system as a laboratory. The gravitational dynamics of the solar system extend beyond classical orbital mechanics, revealing intricate patterns of tidal forces and waves that influence the interactions between celestial bodies. These gravitational tidal waves are manifestations of what is termed here as the relative equilibrium between massive objects, such as the Sun, planets, and moons, and the dynamic forces that govern their motion. This exploration delves into the theoretical framework of relative gravity, a model that redefines gravity as a dynamic relationship expressed through relative force, rather than as a static attraction. By examining the interplay of gravitational tidal forces within the solar system, this work seeks to uncover the underlying principles that govern celestial mechanics, including the distribution of energy, the effects of resonant frequencies, and the harmonic synchronization of bodies. Key topics include relative equilibrium, the balancing act between bodies as they exchange gravitational force in oscillating cycles, forming a complex network of relationships across the solar system. Resonant frequencies, how gravitational waves create harmonics that contribute to the organization and placement of celestial bodies. Gravitational impedance and wave propagation, the resistance and transfer of gravitational energy through a medium, analogous to electromagnetic wave behaviors. Practical implications, how understanding gravitational tidal waves could enhance models of planetary formation, orbital stability, and interplanetary dynamics. By bridging classical and modern frameworks, this study aims to provide a comprehensive understanding of gravitational tidal waves as a unifying concept that connects the micro and macro scales of the universe. This research promises insights into the dynamic relationships that sustain the balance and harmony of the solar system, offering profound implications for both theoretical physics and practical applications in space exploration. 3.1. Introduction to relative equilibrium and gravitational tidal waves. The universe operates as a dynamic, interconnected system of gravitational forces. Every celestial body, from planets to stars to galaxies, exerts an influence on its neighbors. Understanding how these forces interact is essential to explaining the intricate dance of objects in space. Among the most intriguing aspects of this cosmic ballet is the concept of relative equilibrium, a theoretical framework that allows us to pinpoint the balance of gravitational forces between two or more celestial bodies. This project explores the implications of RE within our solar system and introduces a groundbreaking hypothesis: the existence of gravitational tidal waves, dynamic patterns shaped by the interplay of RE points over time. 3.2. Objectives. Develop a computational model to calculate and visualize RE points dynamically over time. Demonstrate how these RE points form wave-like patterns, revealing the existence of gravitational tidal waves. Extend the model to include all planets in the solar system, creating a comprehensive map of interplanetary tidal forces. Provide a foundation for scaling this framework to larger systems, such as galaxies or intergalactic structures. 3.3. What is relative equilibrium? Relative equilibrium refers to the dynamic point in space where the gravitational forces between two celestial bodies balance each other. Unlike traditional gravitational models that focus on a single dominant force, acknowledges the contributions of both bodies' masses and distances, providing a nuanced perspective on gravitational interactions. For example, in the Sun-Earth-Mars system, the Sun exerts a dominant gravitational pull on Earth and Mars due to its massive size. Earth and Mars also exert smaller, yet measurable, gravitational forces on each other. The repoint between Earth and Mars is the location where their gravitational forces are in balance, considering the Sun's influence as the overarching force. This equilibrium point is not static, but shifts dynamically as the planets move in their orbits, creating a wave-like pattern that reflects the gravitational interplay over time. 3.4. Why use relative equilibrium? Traditional gravitational models, such as Newton's laws or Einstein's general relativity, often simplify multi-body systems by focusing on dominant forces or treating smaller forces as negligible. While effective for many calculations, these approaches overlook the subtler dynamics that arise in complex systems like the solar system. Relative equilibrium offers several advantages. 1. Captures multi-body interactions. By considering the relative masses and distances of multiple bodies, provides a more complete picture of gravitational dynamics. 2. Reveals dynamic patterns. The shifting repoints reflect the gravitational waves created by moving celestial bodies, offering insights into the interconnected nature of their orbits. 3. Extends beyond local systems. The framework can scale from planetary systems to galaxies, providing a unified approach to understanding gravitational interactions across scales. 3.5. Gravitational tidal waves, the hypothesis. This project posits that the dynamic shifts and repoints create gravitational tidal waves, oscillations and gravitational forces that propagate through the system. These waves are not ripples in spacetime as described by Einstein, but rather dynamic fluctuations in gravitational potential within the system. By visualizing the repoints between planets like Earth and Mars, we can observe the wave-like behavior of the repoints as they shift with planetary motion, how these waves interact with other planetary systems, creating a web of gravitational dynamics within the solar system. 3.6. Relative equilibrium compared to Kepler's center of gravity. Kepler's center of gravity simplifies gravitational interactions to a single point determined by the masses and distances of two bodies. Relative equilibrium builds on this by integrating dynamic interactions with additional celestial bodies, providing a more intricate and accurate depiction of gravitational forces in multi-body systems. Relative equilibrium is the balance point between two celestial bodies where their gravitational forces are equal and opposite, described as. These balance points, or repoints, shift dynamically as planets move through their orbits, forming a rich tapestry of gravitational interactions. By mapping these repoints over time, intended is to uncover the tidal waves of gravitational influence that connect the Sun, planets, and even moons in a grand celestial rhythm. 3.7. The significance. This work not only can deepen our understanding of gravitational dynamics within the solar system, but also lays the groundwork for future studies in astrophysics. By uncovering the existence of gravitational tidal waves, we can redefine how we think about the forces shaping our universe, from the smallest planetary systems to the largest galactic clusters. 3.8. Demonstrating the Earth-Sun model. To understand relative equilibrium, please consider the interaction between the Earth and the Sun as a two-body system where their gravitational forces dictate the relative motion of Earth in its orbit. While the Sun's mass dominates the interaction, Earth also exerts a smaller yet measurable gravitational influence. Relative equilibrium is the theoretical point where the gravitational forces between two bodies balance. For Earth and the Sun, this point exists along the line connecting their centers of mass, factoring in the Sun's relative mass and its gravitational pull on Earth, Earth's relative mass and its counteracting pull toward the Sun. The distance between them d, which influences the magnitude of their respective gravitational forces. For example, md2 equals md1 where d1 is the distance from the Sun to the repoint. d2 equals d minus d1 is the distance from Earth to the repoint. 3.9. Substituting Newton's law of gravitation. This model extends Newton's framework by incorporating the dynamic shifts in repoints due to orbital changes. This introduces a layer of complexity that can account for wave-like patterns observed in redynamics. m1 d2 equals m2 d1. Solving this equation provides the location of the repoint relative to Earth or the Sun, allowing us to quantify where their gravitational forces achieve balance. Essential to Kepler's, Newton's, and Einstein's thinking is the idea of the center of mass. Re was originally inspired based on this, but it is in a way to account for measuring the force between what are referred to as relative masses instead. The center of mass for two bodies, the Earth and Sun, is outlined below. Mass 1 distance 1 equals mass 2 distance 2 where r equals total distance equals d1 plus d2. For Kepler et al., let d1 and d2 be as d1 equals rm1 plus m2 and d2 equals rm1 plus m2 Dynamic behavior of the repoint. As Earth follows its elliptical orbit, the distance between Earth and the Sun changes, causing the repoint to shift dynamically over time. This motion of the repoint forms a wave-like pattern, influenced by the eccentricity of Earth's orbit. Variations in orbital speed as Earth moves closer to or farther from the Sun. 3.10. Dynamic relative equilibrium between the Sun and Earth. The above plot visualizes the concept of relative equilibrium Re in the Sun-Earth system over the course of a year 2025. This analysis provides critical insights into the wave-like nature of repoints, revealing dynamic gravitational relationships that fluctuate as celestial bodies move through space. Key elements of the plot. 1. Earth-Sun distance blue line. This curve represents the heliocentric distance of Earth from the Sun, measured in astronomical units O. The slight oscillation in the Earth-Sun distance illustrates the elliptical nature of Earth's orbit, where its proximity to the Sun changes slightly over time, from perihelion closest point to aphelion farthest point. 2. Relative equilibrium point green dashed line. The repoint is calculated based on the Sun and Earth's masses and the inverse square gravitational relationship between them. This point fluctuates dynamically and follows a wave-like behavior, maintaining a consistent proportional relationship relative to the Earth-Sun distance. Sun and Earth positions markers. The orange markers represent the position of the Sun as a fixed reference point. The blue markers highlight Earth's position at the beginning and end of the year, indicating that the orbit is both periodic and predictable. Interpretation of the wave-like behavior. The wave-like nature of the relative equilibrium repoint is a direct result of the interplay between gravitational forces and the relative motion of the Earth and the Sun. As Earth travels along its elliptical orbit, the repoint shifts closer to the Sun during Earth's perihelion, where its distance from the Sun is minimized. Conversely, the repoint shifts slightly farther during Earth's aphelion. This consistent oscillation demonstrates the dynamic stability of gravitational systems, where forces adjust naturally to maintain equilibrium over time. 1. Gravitational tidal waves. The oscillations of the repoint relative to the Earth suggest the existence of subtle gravitational tidal waves. These waves, while imperceptible on short timescales, illustrate how forces interact and propagate across space, maintaining equilibrium. 2. Predictive modeling. By accurately plotting the repoints, we can gain predictive power in understanding how gravitational forces shape orbital mechanics. This framework is extensible to other planetary systems, enabling broader applications. 3. Bridging theory and observation. The plot serves as an illustrative example of the principles underlying relative gravity, showcasing its ability to describe and predict dynamic behaviors within the solar system. It connects abstract mathematical formulations to tangible phenomena. In the Sun-Earth model, the concept of the relative equilibrium repoint goes beyond mere mathematical abstraction, suggesting profound physical and observational implications. Using the formula outlined m1d2 equals m2d1. As calculated, it is the location where the gravitational forces of the Sun and Earth achieve a balance. This point represents the dynamic boundary where gravitational forces between these two celestial bodies are in harmony. However, the implications extend far beyond gravitational theory. 3.11. Physical alignment with Earth's magnetosphere. The repoint in the Sun-Earth system aligns intriguingly with Earth's magnetosphere, the region dominated by Earth's magnetic field and influenced by solar wind. This magnetosphere serves as a shield, protecting the planet from charged particles emanating from the Sun. The interplay between gravitational forces and the magnetosphere at the repoint suggests a deeper linkage between gravitational and electromagnetic dynamics. This connection offers a unique perspective on how such forces might work in tandem to shape planetary environments. 3.12. Connection to the Northern Lights. The repoint's alignment with the magnetosphere introduces another fascinating phenomenon, the Northern Lights aurora borealis. These mesmerizing displays of light occur when charged particles from the Sun collide with Earth's magnetic field, funneling energy toward the polar regions. The repoint is a dynamic gravitational balance, coincides with the region where solar wind energy interacts most significantly with Earth's magnetosphere, driving these charged particles into the atmosphere. This overlap provides a tangible observational aspect to the Re theory, linking gravitational equilibrium to visible, real-world phenomena. 3.13. Observing the dynamic behavior of the repoint. The wave-like behavior of the repoint as depicted in the plots reflects its dynamic nature. Over the course of a year, the repoint shifts subtly in response to the orbital changes of the Earth. These shifts mirror the oscillations seen in the magnetosphere and align with fluctuations in solar activity, suggesting that the repoint is not only a static balance, but also a dynamic contributor to planetary and solar interactions. 3.14. Proof of vision. The Sun-Earth model offers a powerful demonstration of the principles of relative equilibrium, bridging theoretical calculations with physical observations. The alignment of the repoint with Earth's magnetosphere and its connection to phenomena like the northern lights exemplifies the tangible implications of this theory. By visualizing these interactions, we can not only deepen our understanding of gravitational dynamics but also gain insight into the interconnectedness of forces shaping our solar system. 3.15. Introducing relative equilibrium in multi-body systems. The Earth-Sun example lays the foundation for understanding relative equilibrium in a two-body system. However, in the context of multi-body systems, such as Earth-Mars-Sun, the dynamics become more complex and captivating. The repoint is shaped by the interplay of gravitational forces between Earth and Mars, the overarching influence of the Sun's gravitational pull, which remains dominant yet allows Earth and Mars to interact gravitationally within its sphere of control. 3. Calculate the repoint between Earth and Mars. We need to balance their gravitational forces in the context of the Sun's gravitational field, Earth equals F Mars. This calculation ensures that the repoint is not merely a static location, but a dynamic one that shifts as Earth and Mars traverse their respective orbits. The result is a gravitational tidal wave, a ripple in the fabric of their shared gravitational field, oscillating over time. Visualizing this repoint reveals a wave-like behavior as Earth and Mars move through their elliptical paths. Visualization of the relative equilibrium repoint between Earth and Mars, showing their elliptical orbits, the gravitational tidal wave, and the dynamic shifts in the repoint. This dynamic wave is not merely a mathematical construct, but a physical reality, representing the equilibrium point as periodic oscillation. Such oscillations are a direct consequence of the interplay between planetary masses, distances, and the Sun's gravitational dominance. The Earth-Mars repoint offers a striking example of gravitational interaction in multi-body systems. By plotting the Earth-Mars-Sun system, we can observe the distances of Earth and Mars from the Sun, the dynamic repoint as it oscillates between them, creating a gravitational wave. This wave-like behavior of the repoint provides insight into the complex gravitational interactions within our solar system, demonstrating that relative equilibrium is not merely a theoretical framework, but a tangible mechanism that influences celestial dynamics. This dynamic equilibrium produces a shifting repoint, creating a gravitational tidal wave as Earth and Mars traverse their orbits. 3.16. Expanding relative equilibrium to multi-body systems. The concept of relative equilibrium, as introduced in two-body systems, serves as a powerful foundation for understanding the intricate gravitational dynamics in multi-body systems. By extending this framework, we can explore the dynamic interplay of forces in more complex configurations, such as those involving multiple planets and their respective orbits. A. Circular orbits and relative equilibrium. The first visualization demonstrates the redynamics among three adjacent planets, Mars, Earth, and Venus. Each planet follows an elliptical orbit around the Sun, which has been approximated here as circular for clarity and simplicity. The key features of this representation include planetary orbits. Mars' orbit is depicted as the largest red circle, reflecting its greater average distance from the Sun. Earth's orbit is shown as the intermediate blue circle, positioned between Venus and Mars. Venus' orbit is represented as the smallest orange circle, highlighting its closer proximity to the Sun. Relative equilibrium lines. The dashed green line denotes the repoints between Mars and Earth. The dotted purple line represents the repoints between Earth and Venus. The repoints for each pair are calculated using the relative masses and distances of the planets, as defined by the equation. These equilibrium lines provide a spatial representation of the balance of gravitational forces between the planets. The visualization emphasizes how the planets' gravitational fields interact dynamically while orbiting the Sun. Such relines are not fixed but shift slightly due to orbital eccentricities and relative motion, forming what can be interpreted as gravitational tidal waves over time. B. Elliptical orbits and temporal dynamics. The second visualization transitions from spatial representation to temporal analysis, focusing on the distances of planets from the Sun and their respective repoints over a one-year period, 2025. This dynamic model includes 1. Planetary distance oscillations. The blue, red, orange, and purple lines track the heliocentric distances of Earth, Mars, Venus, and Jupiter, respectively. These oscillations reflect the elliptical nature of planetary orbits, where distances vary with time. 2. Relative equilibrium dynamics. The dashed green line illustrates the re-points between Mars and Earth. The dashed dotted brown line captures the re-points between Jupiter and Saturn, representing interactions in a more massive outer planetary system. 3. Wave-like behavior. The re-points exhibit oscillatory behavior, creating wave-like patterns. These patterns highlight the dynamic equilibrium as planetary configurations evolve. 3.17. Significance of the visualizations. A combination of these two visualizations, spatial orbits with relines and temporal dynamics, provides a comprehensive understanding of multi-body gravitational interactions. Together they illustrate 3.17.1. Interconnected gravitational dynamics. Relines reveal how gravitational forces interact across multiple bodies, creating zones of balance that shift dynamically with orbital motion. 3.17.2. Gravitational tidal waves. The oscillatory patterns in the re-points suggest the presence of gravitational tidal waves, a phenomenon that encapsulates the rhythmic propagation of gravitational forces through the solar system. 3.17.3. Framework for predictive analysis. By mapping re-points over time and space, these models lay the groundwork for predicting gravitational interactions in both local and broader cosmic contexts. They also provide insights into the stability and dynamics of multi-body systems, from planetary orbits to galactic structures. 3.18. Bridging relative equilibrium and general relativity. Einstein's theory of gravity, or general relativity, fundamentally transformed how we perceive gravity, not as a force in the traditional sense, but as a curvature in the fabric of spacetime caused by mass and energy. Illustration of general relativity, depicting spacetime curvature and gravitational waves from merging black holes. This curvature guides the motion of objects, creating what we perceive as gravitational interactions. The dynamic nature of spacetime and general relativity leads to phenomena such as gravitational waves, ripples in spacetime that propagate outward from massive objects undergoing acceleration, like merging black holes. In the context of gravitational tidal waves within the solar system, the comparison with Einstein's framework raises fascinating questions. 1. Dynamic tidal patterns versus spacetime ripples. Gravitational tidal waves, as hypothesized in the relative equilibrium reframework, represent oscillations in the gravitational potential of a system caused by the shifting balance of gravitational forces between celestial bodies. Unlike Einstein's gravitational waves, which are disturbances in spacetime itself, these tidal waves are more localized phenomena, reflecting the interaction of gravitational forces in multi-body systems. 2. Relative equilibrium and general relativity. While general relativity provides a universal description of gravity, its equations are often complex and computationally intensive for multi-body systems. The reapproach offers a complementary perspective by focusing on the dynamic balance of forces in specific systems, making it more practical for visualizing interactions within planetary systems. This is particularly useful in studying systems like Earth, Mars, Sun, where the re-points reveal the intricate gravitational relationships. 3. Observable implications. General relativity predicts phenomena like frame dragging and gravitational time dilation near massive objects. In contrast, gravitational tidal waves as proposed here are macroscopic and arise from the cumulative gravitational forces of multiple bodies. They may not distort spacetime in the relativistic sense, but instead manifest as patterns of gravitational equilibrium that shape the motion of celestial objects and possibly influence other physical phenomena, like electromagnetic interactions. 4. Bridging the frameworks. While general relativity is the cornerstone of modern gravitational theory, the re-framework could serve as a practical tool to identify and study specific interactions, providing a bridge between theoretical predictions and tangible observations. For instance, the re-point disalignment with Earth's magnetosphere could hint at connections between gravitational and electromagnetic fields, something that general relativity does not directly address. The concept of gravitational tidal waves enriches our understanding of how celestial systems operate on a macro scale. While they are not ripples in spacetime as per Einstein's theory, they provide a compelling narrative for how gravitational dynamics unfold over time, adding a new layer of understanding to the cosmic dance of masses and forces. By integrating the insights from both frameworks, we can open doors to a more holistic view of the universe, where theoretical elegance meets observational clarity. 3.19. Relative equilibrium as the bridge to relative gravity. Newton's law of gravitation revolutionized our understanding of celestial mechanics by introducing the gravitational constant. G is a universal scalar. m1 and m2 are masses, r is the distance between them, and g is the gravitational constant 6.6743 plus or minus 0.00015 times 10 minus 11 m3 kg minus 1 s minus 2. However, Newton's SG is static, Earth-centric, and unable to adapt to the dynamism of multi-body systems. By contrast, relative gravity RG, expressed through relative equilibrium RE, provides a flexible and dynamic approach to understanding gravitational interactions. 3.20. Writing gravity in terms of relative equilibrium. Using the framework of relative gravity, the relationship is instead defined as: here, Re represents relative equilibrium, the dynamic balance of forces between celestial bodies. E infinity T infinity reflects energy and time squared, highlighting their interplay in spatial time. D2 infinity, the spatial distance between bodies, integrates gravitational influence over a dynamic range. This formulation replaces the static G with Re, which evolves dynamically as masses and distances change in multi-body systems. 3.21. Energy, time, and distance in spatial time. In relative gravity, energy E and time T are interdependent, emphasizing that gravitational dynamics operate not in isolation, but within a continuum of spatial time. The term E infinity T infinity, averaged across interacting bodies, introduces a relativistic layer to gravitational calculations, showing how energy evolves as time progresses. The inclusion of Re within this framework captures the dynamic balance of gravitational forces. Re equals m1d2 equals m2d2, where d1 and d2 represent distances from the equilibrium point to the respective bodies. This proportional relationship explains how Re governs the shifting points of gravitational balance between celestial bodies. 3.22. Why replace G? Dynamic behavior, unlike G, which assumes static relationships, Re adapts to the continuous motion of celestial bodies, reflecting gravitational changes in real time. Multi-body systems. Traditional models simplify multi-body systems into isolated pairs, while Re incorporates all relevant interactions, enabling more accurate predictions of gravitational forces. Wave-like patterns. As seen in gravitational tidal waves, Re points oscillate dynamically due to the interplay of masses and distances, creating patterns that cannot be captured with grams. 3.23. Implications for gravitational tidal waves. The oscillating Re points, as calculated and visualized, reveal the presence of gravitational tidal waves. These are not spacetime distortions like Einstein's gravitational waves, but dynamic variations in gravitational potential, reflecting the interplay of energy, time, and distance within the system. 3.24. Revolutionizing gravitational theory. By integrating Re, relative gravity offers a more comprehensive framework for understanding the universe. From local to cosmic, Re scales seamlessly from planetary systems to galaxies, providing a unified approach to gravitational interactions. Dynamic insights. The inclusion of energy, time, and spatial relationships can deepen our understanding of gravitational forces as dynamic phenomena, not static constants. Observable impacts. Phenomena like gravitational tidal waves and their interactions with magnetospheres link theoretical predictions to tangible observations. Conclusion. Relative equilibrium does more than replace Newton's SG. It redefines gravity as a dynamic, evolving force shaped by energy, time, and distance. The formula Rg equals Re E infinity T infinity 2 provides a foundation for this new understanding, connecting abstract theory with observable phenomena. Visualization of relative equilibrium Re points and their oscillations, illustrating the convergence of classical, relativistic, and quantum perspectives into a unified framework. By visualizing Re points and their oscillations, we can uncover a richer tapestry of gravitational dynamics, bridging classical, relativistic, and quantum perspectives into a unified framework. 4.0. Beyond planets, gravity in deep space. With Rg, we can reimagine gravity's role in deep space. Instead of assuming an absence of gravity in interstellar regions, proposed in Rg is a self-balancing force, a kind of gravitational breathing that dynamically adjusts to its surroundings. This concept allows us to see weightlessness not as the absence of force, but as a state of equilibrium, a balance between competing gravitational influences. 4.1. Gravitational waves in the Rg framework. In Einstein's general relativity (GR), gravitational waves are considered ripples in spacetime curvature caused by accelerating massive bodies. In contrast, relative gravity (RG) views gravitational waves as periodic fluctuations in equilibrium states rather than distortions in spacetime. Illustration of gravitational waves within the relative gravity framework highlights wave patterns, impedance fields, and wave interference zones. What this means in RG framework. For RG, gravitational waves do not bend spacetime. Instead, they oscillate as shifts in gravitational balance between masses. The waves propagate through fields of gravitational impedance, similar to how sound waves travel through air, but in this case, they move through the interplay of energy, time, and mass distributions. Relative equilibrium redynamically adjusts, much like an alternating current AC system, rather than a permanent geometric distortion. 4.2. Demonstrating RGS explanation of gravitational waves. To illustrate how RG naturally accounts for gravitational waves, let us examine the case of binary star systems and how they produce gravitational fluctuations. Newtonian GR view. In general relativity, two orbiting massive bodies, for example neutron stars, create gravitational waves by distorting spacetime, causing energy loss and orbital decay. The energy loss rate is given by the classic quadrupole formula from Einstein's general relativity. dk equals minus 32.5 gcm1 m22 m1 plus m2a5. d energy loss per unit time power radiated. G Newton's gravitational constant. C speed of light. m1 m2 masses of the binary stars. A orbital separation. This equation implies that the orbital separation decreases over time, leading to a faster orbit and stronger gravitational waves. RG view. Instead of spacetime distortion, RG explains these waves as oscillations in the equilibrium state between the two masses. The system's relative equilibrium adjusts periodically due to mass-energy redistribution, changes in the distribution of mass-energy, orbital momentum variations, adjustments in angular momentum due to energy exchange, force exchange dynamics, alternating phases of attractive and resistive forces within the system. Mathematical representation. In Newtonian terms, F equals gm1 m2 r2. In RG terms, for relative equilibrium, for ET equals ET CR cos 2 pi F E plus letter, free, D5. The equilibrium fluctuates periodically as mass-energy interactions create wave-like motion and force balance, producing what we perceive as gravitational waves. For ET, time-dependent force in the RG framework. ET, time-dependent energy exchange derived from mass-energy equivalence. C. Speed of light as a scaling constant r, orbital separation f, oscillation frequency related to the orbital period letter, for ET5, phase shift. 4.3. In retrospect. A. No need for spacetime curvature. RG treats space as a structured but fluid-like equilibrium field, rather than a fabric that bends. B. Explains wave energy transfer. Instead of gravitational waves stretching space, they cause oscillations in the balance between celestial bodies. C. Unifies with other wave phenomena. This approach aligns gravitational waves more closely with electromagnetic waves and acoustic waves, making RG compatible with known physics of wave propagation. D. Predicts measurable effects. In this framework, detecting gravitational waves involves measuring shifts in relative equilibrium over time, rather than observing space-time distortions. 4.4 Implications for black holes' deep space structures. Black holes in RG are regions of extreme reshifts, rather than singularities that warp spacetime. Interstellar gravity fields create overlapping equilibrium zones, preventing truly empty space. Dark matter may be an impedance effect, regulating mass distribution in larger-scale structures. This realization naturally led us to a frontier that has long haunted physics: black holes. 5. Black holes as spatial induction engines. For decades, black holes have been defined by their mysteries: regions where gravity becomes infinite, where time stops, where matter collapses into an unknowable singularity. But what if singularities don't exist at all? What if black holes, rather than being dead zones of infinite density, are instead spatial induction engines, self-regulating systems that transform, rather than destroy, matter and energy? 5.1 Gravity at the event horizon. Through RG, we can discover that gravity at the event horizon does not become infinite. Instead, it reaches an equilibrium state, a balance point where mass energy doesn't vanish into an abyss but cycles through a process of spatial induction. This insight explains why quasars emit extraordinary amounts of energy while powered by black holes. Why black holes seem to regulate, rather than merely consume, space around them. How energy and mass undergo a process of resonance rather than pure collapse at the event horizon. 5.2. The spatial induction model. A black hole as an energy regulator. Traditional theories suggest that nothing can escape a black hole, and that all matter is crushed into a singularity. However, observations of high-energy emissions jets and accretion dynamics suggest that black holes do not merely consume but actively regulate energy exchange. In the spatial induction engine model, a black hole functions as an A. Energy transformer. Mass energy entering a black hole is not destroyed but transformed into a new state that resonates with surrounding gravitational fields. B. Gravitational resonance system. Rather than a singularity, the core of a black hole may oscillate between equilibrium states. similar to a harmonic oscillator. C. Spatial current generator. Black holes may induce alternating gravitational currents AGC influencing surrounding space. This means that black holes do not disrupt space, they maintain and reshape it through regulated energy induction. 5.3. RGS black hole model with Einstein's fundamental differences. Einstein's general relativity GR defines black holes as regions where spacetime curves infinitely, leading to a singularity where all known physics breaks down. Relative gravity RG, by contrast, proposes that singularities do not exist. Instead, black holes maintain an internal equilibrium, where energy and mass cycle through spatial induction processes. Model Einstein's view GR relative gravity RG. Nature of the event, a point of no return in equilibrium boundary horizon. Infinite collapse into matter behavior inside resonant transformation singularity. No explanation for energy emission due to induction affects jets. Equilibrium stabilizes black hole stability, singularities are unstable behavior. RGS model provides a self-regulating mechanism, removing the paradox at infinite densities. 5.4. Observational evidence supporting the spatial induction model. RG predicts that black holes should exhibit measurable energy cycling and equilibrium-driven emissions, aligning with real astrophysical data. Observations that support this include: A. Quasar energy emissions. The extreme brightness of quasars suggests that energy is being regulated and emitted, rather than infinitely compressed. B. Black hole jets. High-energy plasma jets emerge from black hole poles, a phenomenon not fully explained by Einsteinian physics, but natural in an induction-based framework. C. Event horizon stability. Black hole mergers generate stable gravitational wave harmonics, suggesting non-singular equilibrium effects rather than infinite collapse. These confirm RGS' hypothesis that black holes act as spatial induction engines, rather than one-way destruction zones. 5.5. The role of alternating gravitational currents AGC in black hole stability. Alternating gravitational currents AGC play a crucial role in black hole equilibrium. AGC ensures that mass energy oscillates within the event horizon, rather than collapsing into a singularity. The event horizon behaves like a resonant cavity, regulating mass energy exchange dynamically. The surrounding spacetime is stabilized by these oscillations, preventing runaway collapse. This supports the idea that black holes are not endpoints, but energy processing systems within the cosmic structure. 5.6. The implications: black holes as cosmic architects. By treating black holes as spatial induction engines, we can redefine their role in cosmic evolution. They are not destructive voids but energy regulators that structure galaxies. Their interactions with surrounding spacetime explain galactic dynamics and cosmic web formations. Their emission patterns suggest that energy is not lost but transformed, fueling interstellar and intergalactic processes. This new model suggests that black holes play an active role in shaping cosmic structures, rather than being mere endpoints of gravitational collapse. 5.7. Conclusion: a shift in the common understanding of gravity. For RG, black holes do not contain singularities, but equilibrium states that induce energy transformations. The spatial induction engine model removes the paradox of infinite densities. Energy and mass cycle within black holes, rather than vanishing into a singular point. This model aligns with observed black hole emissions, jets, and stability patterns. This revolutionary perspective on black holes bridges gaps between gravity, energy transformation, and cosmic structure formation, providing a new paradigm for understanding the role of black holes in the universe. 5.8. Supporting equations and examples. A. Relative gravity and black hole equilibrium. Rather than a singularity, a black hole maintains an equilibrium governed by ReBH equals MBH/RH plus M inf R-inf, where ReBH is the relative equilibrium of the black hole, MBH is the mass of the black hole, RH is the event horizon radius, M-inf is the mass energy of infalling material, R-inf is the radius at which mass energy interacts with the black hole. B. Spatial induction process. The interaction of mass energy with the black hole follows an alternating current-like oscillation. E out equals E in E it costs 2 pi, where E in E is the infalling energy. E out is the emitted energy as seen in quasars. Letter 1, B, 4 is a damping coefficient dependent on relative equilibrium. T is time. This equation explains why black holes emit structured energy outputs such as quasar emissions, gamma-ray bursts, periodic energy ejections, Hawking radiation-like effects from equilibrium stabilization. C. Why gravity does not become infinite. Instead of an infinite collapse, RG predicts a maximum gravitational threshold. GMBH/RH equals C, where G is Newton's gravitational constant. C is the speed of light. MBH equals mass of the black hole. RH equals event horizon radius. is the mass of the black hole. This implies that instead of an infinite singularity, a black hole stabilizes at an equilibrium limit, preventing unbounded gravitational collapse. D. Key implications. Black holes are not singularities, but dynamic equilibrium systems. They regulate mass energy through a spatial induction process. They emit structured energy, explaining quasars and relativistic jets. Their gravitational pull stabilizes, preventing infinite density. By treating black holes as self-regulating equilibrium systems, RG provides a revolutionary alternative to singularities, reconciling observations with a dynamic gravitational model that aligns with astronomical data.